You know how it is. You want to wrap your head around something complex in the tech world, right?
Yeah, absolutely.
But the thought of slogging through endless articles and, well, research papers, it can feel overwhelming.
Definitely.
That's why you're here, and that's exactly what we do. Welcome to the deep dive. We take a dense stack of information, in this case, a really insightful transcript, and extract the key nuggets you need to know quickly and clearly.
Exactly. And today, we're diving deep into the core technology that is really fueling this incredible AI revolution you're seeing pop up, well, pretty much everywhere.
It's
It's
everywhere.
not just in the big flashy news either.
Hmm.
It's quietly changing the apps you use every day
Yeah,
and opening up entirely new possibilities.
you got it. And the transcript we've been looking at really paints a vivid picture of this transformation.
It does.
Think about how you might have approached a coding problem a few years ago, probably heading straight to Stack Overflow, right?
Oh, for sure. The go-to.
Now, coding assistants powered by AI are stepping right in. Or consider creative fields. Generative AI is fundamentally reshaping tools like Photoshop and Figma.
Big time. Even basic stuff like grammar checking.
Mhm.
Grammarly was great, but now you might just ask ChatGPT.
Exactly. It feels like a sidekick sometimes. And it keeps going. Video creation, drafting emails, even just finding a better way to say something. AI is sort of reinventing it all.
And what's truly fascinating, as this transcript highlights, is that this isn't just about a wave of new products hitting the market.
No, it's deeper.
It is. AI is fundamentally altering the very processes we use to create things, whether that's written content, videos, or images.
Right.
And as the direct result, the skills that are valuable and the job roles that are in demand are also undergoing a pretty significant shift,
Yeah.
something people are likely seeing firsthand.
Take Photoshop, like you mentioned. You used to have to master all these incredibly intricate layering techniques,
Yeah.
hours and hours.
Oh, yeah. Complex stuff.
Now, generative fill, powered by AI, basically bypasses a lot of that complexity. It's democratizing image manipulation in a way we haven't really seen before.
It really is. And then look at video. The transcript touches on these early-stage visual effects tools like Runway ML and Pika Labs.
Yeah, what about those?
Well, they're hinting at a future where creating high-quality video content could be completely revolutionized. Think about the impact on filmmaking, social media, everything.
Wow. Okay, so if we pull back a bit, connect this rapid change to the bigger picture, it naturally brings us back to a really fundamental question, doesn't it? One that Alan Turing posed years ago. Can machines think?
The classic question.
Mhm.
And as the transcript points out, the entire journey of AI development since then has essentially been about trying to answer that, figuring out how to teach machines to think, or at least, perform tasks like thinking.
Okay, let's unpack one of the key turning points mentioned in the transcript. It highlights the explosion of internet data after, 1993.
Right around then, yeah. Suddenly, there was just this massive, almost unimaginable amount of information online. Text, images, everything.
And the sheer volume of data sparked a crucial idea, didn't it?
It did. Could we leverage this ocean of information to teach machines? Could they learn by recognizing patterns within it?
So how do we actually get machines to find these patterns in all that data?
Well, that's where, as the transcript introduces, fields like data analysis, data science, and machine learning came into play.
Okay.
At their core, these fields are all about developing methods to extract meaningful patterns and insights from, well, just vast amounts of raw data. Increasingly vital now.
So the first stab at this, the transcript explains, involved what are called rule-based or expert systems.
Yeah, exactly. Think of it like trying to teach a computer to recognize the numbers 0 and 1. You give it very specific instructions based on their shapes.
Like if it's a closed curve, it's a 0. If it's a vertical line, it's a 1. Simple rules. Simple, exactly. But what's fascinating, and the transcript illustrates this well, is how quickly those limitations become obvious when things get more complex.
Right, like a tilted 0. Or different faces.
Precisely. The transcript uses the example of a 0 that's slightly tilted, or just the immense variability in human faces. Suddenly, your neat little set of rules just explodes.
It becomes unmanageable.
Totally unmanageable.
Yeah.
How many rules would you need for every angle of a face? Different lighting, maybe someone wearing glasses or a hat. It just becomes impractical very, very quickly.
Yeah, okay, I see. And that's precisely where traditional machine learning algorithms came in, according to the transcript.
That's the next step. It was a move beyond those rigid, manually defined rules towards more abstract, mathematically sophisticated ways for machines to recognize patterns.
More flexible ways.
Exactly. The transcript briefly mentions techniques like clustering, grouping similar data points, and principal component analysis, which helps simplify complex data. Basically, more powerful tools for understanding information. Okay, building on that, the transcript then brings up reinforcement learning. This sounds interesting learning like we do.
It's a really intuitive idea, yeah.
Yeah.
Much like how we learn from experience, the classic example is a child touching a hot stove.
Ouch. Yeah.
That negative feedback, the pain, teaches them not to do it again. Reinforcement learning works on a similar principle.
So learning through interaction.
Exactly. The transcript uses the Mario example from the video game.
Ah, Mario. Okay.
When he eats a mushroom, he gets a positive reward, he grows bigger. So in reinforcement learning, you have an agent, Mario, taking actions, eating a mushroom within an environment, the game world, and receiving rewards, positive or negative.
Okay, agent, action, environment, reward.
Got it. And that's used in things like robotics.
Yeah, robotics. Autonomous agents that need to learn to navigate, make decisions in complex situations. It's powerful for that kind of interactive learning.
But the real game changer the transcript seems to emphasize came with neural networks, sometimes called perceptrons. Yes, absolutely. Because even traditional machine learning had limitations in capturing the real subtleties of the world, context, intentions, the environment, things that aren't easily defined by simple patterns.
So neural networks were needed for that deeper complexity.
Exactly. The transcript describes them as these vast, interconnected webs of mathematical equations. Imagine a huge network of nodes.
Like neurons in a brain? Kind of.
It's sort of inspired by that, yeah.
Yeah.
Each node does a relatively simple calculation, but when you link millions of them together in multiple layers, they become capable of learning incredibly complex relationships and patterns from data.
And the transcript points out that LLMs and CNNs, the big names we hear about, are just types of these neural networks.
That's right. There are specific architectures, specific ways of connecting those nodes designed for different tasks.
Okay, so how do these massive networks actually learn? It sounds complicated.
Well, the transcript delves into the backpropagation algorithm. In a simplified sense, it's like giving the network feedback when it gets something wrong.
Like correcting it.
Exactly. Think back to a child learning the difference between a cat and a dog. If they point at a fox and say dog, you say, no, that's not a dog.
Right.
That correction, that feedback, helps the child adjust their understanding. Backpropagation is kind of analogous. Errors in the network's output are fed back through the network to subtly adjust its internal connections, its understanding, to make better predictions next time.
Okay, feedback loop. And what really sped this all up, the transcript mentions GPUs, graphics cards.
Yes, this was huge. Graphics processing units. There was this key insight referenced in the transcript, realizing that the core math inside neural networks,
Lots of matrix algebra, apparently.
a ton of matrix algebra, and it turned out that GPUs, originally designed for pushing pixels in video games, were incredibly efficient at exactly that kind of parallel math.
Ah, so they could crunch the numbers way faster than regular processors.
Massively faster. And this dramatic speed up in processing power, it really fueled the incredible progress and breakthroughs we've seen in AI recently. It made training these huge networks feasible.
That makes sense. So building on that, the transcript says deep learning just means using neural networks with lots of layers.
Pretty much deep neural networks. Hence deep learning. And the architecture, basically how you connect all those nodes and organize the layers, is absolutely critical.
Different designs for different jobs.
Exactly. Different architectures are suited for different types of data, like convolutional neural networks, CNNs we mentioned. They excel at analyzing images.
Okay.
While recurrent neural networks, RNNs, were initially designed for sequential data, like text, where the order of words really matters.
Right, language is sequential. But the transcript mentions early RNNs had some trouble.
They did. They often struggled with really long sequences. It was hard for them to remember information from way back at the beginning of a long sentence or paragraph.
Like short-term memory issues.
Yeah, kind of, yeah. Which led to the development of LSTMs, long short-term memory networks. They had a sort of built-in memory mechanism to handle those longer dependencies more effectively.
Okay, so LSTMs improved on RNNs. But then the landscape really shifted again with transformers. That's what the transcript highlights next.
Yes, transformers were a huge leap. A fundamentally different neural network architecture built around this concept called attention.
Attention. What does that mean in this context?
Well, what's fascinating about attention, and the transcript explains this, is that it allows the network to weigh the importance of different parts of the input data as it's processing it.
So it can focus on the relevant bits.
Exactly. It's like the network can selectively pay attention to the most important pieces of information for the task at hand.
And transformers brought some big advantages, the transcript says.
Huge advantages. One key thing is parallel processing. They can process different parts of the input data simultaneously.
Which means faster training.
Much faster training, especially with massive data sets. Plus, they handle long sequences much better than earlier models, and they turn out to be exceptionally good with text data.
Which is why they're everywhere in language AI now.
That's a huge reason, yeah. Their performance with text really led to their widespread adoption.
Okay, this brings us nicely to generative AI. The transcript makes a distinction here from older algorithms.
Right. Traditional algorithms mostly classify data or make predictions based on it.
Like, is this email spam, or what will sales be next quarter?
Exactly. Generative AI goes a step further. These models learn the underlying patterns in existing data, text, images, music, code, and then use that knowledge to create entirely new data that resembles the original.
So not just analyzing, but creating.
Precisely. Generating new content.
And the transcript emphasizes that most of the popular AI tools we see now, ChatGPT, Midjourney, Stable Diffusion.
Even foundational models like Llama. Yep, they're largely built on either transformer architectures or a related technique called diffusion models, or sometimes a combination.
Okay, so let's really try to demystify these large language models, LLMs like ChatGPT. The transcript walks through the process.
It does. At the most basic level, you give them words, text as input.
Like a prompt or a question.
Right. And their main job is to produce words, text as output. Hopefully text that makes sense and is relevant to your input.
But computers don't understand words, they understand numbers. So there's a translation step first.
Crucial first step. As the transcript explains, you have to convert those words into numbers the math can work with. This starts with tokenization.
Tokenization, breaking it down.
Yep. Breaking the input text down into smaller units called tokens. Often words, but sometimes parts of words too. The transcript gives the example, "Hey, how are you doing?" Gets split into several tokens, like, "Hey, Carrie, Harriet, Harriet, Carrie."
Okay, go tokens.
Then what? Then comes embedding creation. Each token gets converted into a high-dimensional vector, basically, a long list of numbers.
High-dimensional vector. Sounds complex.
The transcript uses an analogy. Think of simple 2D or 3D vectors, like coordinates on a graph. Now imagine a graph with hundreds or even thousands of dimensions. Each token gets a unique address in this massive mathematical space.
Okay, an address for each token.
And what's cool, as the transcript notes, is that words with similar meanings tend to end up with embeddings with addresses that are closer together in this space. That helps the model grasp semantic relationships.
And this token stuff is practical too, right? Like how APIs charge.
Exactly. The transcript points this out. Many LLM APIs price their services based on the number of input and output tokens you use. It shows an example with OpenAI's tool, visually breaking down that sentence into tokens.
Okay, so we have tokens turned into numerical embeddings. Where do they go next?
They get fed into the heart of the LLM, that big mathematical equation, the neural network architecture, often a transformer.
And then the LLM predicts what comes next.
Yep, that's the prediction step. Based on the input embeddings and all the text it learned from during training, the LLM assigns probabilities to all possible next tokens.
All of them. Wow.
Well, all the ones in its vocabulary. The transcript uses the example, "I want to go." The LLM calculates the probability for cat, car, home, etc., and usually picks the one with the highest probability to continue the sentence.
Home seems most likely there.
Probably, yeah. But now, the really key question. How does it understand context? How does it know which meaning of a word to use?
Right. The transcript mentioned the word pitch.
Exactly. Great example.
Huh.
Sales pitch, baseball pitch, the pitch in her voice. Completely different meanings. We humans use the surrounding words to figure it out.
So how does the LLM do that?
That's where the attention mechanism comes back in, especially in transformers. The transcript explains it allows the model to weigh the importance of different words in the input when it's figuring out the meaning, the embedding for each specific word.
So for sales pitch, it pays more attention to sales. For baseball pitch, it focuses on baseball.
In essence, yes. It lets the model dynamically focus on the relevant parts of the context to understand the intended meaning and generate a coherent response. The transcript even nods to that key paper, "Attention is all you need."
Okay, so let's quickly recap that LLM process as the transcript laid it out.
Sure.
First, tokenization, breaking input into pieces. Then, embedding creation, turning tokens into numbers, into vectors.
Giving them meaning in that vector space.
Then those embeddings go into the transformer mechanism, using attention to get the context right.
Hmm.
That leads to prediction of the next most likely token.
Based on probabilities.
And finally, response generation, stringing those predictions together to give you the output.
That's the core pipeline, a really fascinating sequence of steps.
It really is. And looking back, as the transcript kind of concludes, it's quite a journey we've traced here.
An incredible journey. From those really basic, rigid if-else rules
Yeah, the simple 0 or 1 rules.
to these incredibly complex, adaptable mathematical representations of language and, well, the world. It's pretty
Yes.
remarkable.
It really brings the key milestones into focus. The absolute importance of data as the starting point.
The fuel for everything.
The core idea of pattern recognition, the evolution of algorithms from rules to stats, then the big leap with neural networks.
Yeah, and the things that made them practical.
Right. Innovations like backpropagation for learning, the sheer power unlocked by GPUs, and that game-changing attention mechanism.
Key enablers, all of them.
So this all leads to a final thought, maybe something for our listeners to chew on.
Yeah.
Now that you have this foundational understanding, this peek under the hood of AI, how might that shift your perspective on just how fast things are changing?
That's a great question. What new possibilities do you see now? What future innovations might build on these core ideas?
It's definitely a fascinating field to keep watching, lots to think about there.